Thank you very much for the lovely introduction, Yin. And yes, I'm waking up. So, but thank you very much for the invitation. I'm excited to present to your community. So the topic for my presentation is artificial intelligence for research, harnessing scientific cyber infrastructure in North America. I will present for probably 15, 20 minutes on AI, and then I'll pass the mic to Derek, and he'll talk about efforts nationally in developing cyber infrastructure. So just wanted to make sure, say thank you. Yes, it's early in the morning for us, but it's definitely a worthy endeavor. So here's a brief outline. I'll introduce artificial intelligence and machine learning. My background is statistics and bioinformatics, so I'll come from sort of a statistical perspective. I'll talk about why we're talking about this, why it's so important. I'm going to skip the recent discoveries and the importance of infrastructure because of time, and also I think you know how important infrastructure is. But I'll have some of those slides in the slide deck that we can share with the community. And then I'll pass to Derek, and he can talk about NSF and their Office of Advanced Cyber Infrastructure. So this is me. This is kind of what we think of as data scientists. This is one of the canonical Venn diagrams that's partly funny, but partly true. Those of us who identify as data scientists have interesting backgrounds, usually a combination of computer science, statistics and mathematics, and some type of domain experience, right? That's the combination. So this is how kind of I think of myself, like, okay, I'm in the middle of this Venn. I think the people I work with mostly would see me as the red star and not so much the yellow star, because they usually will come to me with statistical questions. And so they see me much more on the stat side, as opposed to like the hacking computer science side. But it is an interesting and dynamic and relatively diverse community of people who identify as data scientists. I wanted to highlight that people in the US like me who are academics and scientists, we value international collaborations highly. We think they're extremely important. I love this graph partly because it shows how much the US benefits from foreign-born workforce. We think it's super, super important, all international and domestic politics aside. But that we find international collaborations extremely important and valuable to the work of everyone in the advancement of science. So let me give a little overview of artificial intelligence for as kind of framing information. So when I think of AI, I think of buckets, model buckets, right? So putting models into different areas given their purpose. So instead of AI being just this amorphous big thing of like AI, it's actually underneath a bunch of modeling techniques that serve different purposes. So foundation models, which are the big thing, right? They're the huge models that drive large language like ChatGPT, which every student on the planet is aware of by now. They're designed to learn the distribution of the data. So if it's natural language processing, they're learning how natural language works. If it's a foundation model for capturing images or extracting information from images, they're taking a huge training set and they're trying to learn how those traits are distributed across images, right? So examples, GPT, BERT, which is for natural language processing, ResNet, images, right? So these are big models that usually rely on an enormous training set and tons of training data and take a lot of computing power to develop because they're trying to learn a very complex multidimensional distribution of data. Okay, then you have generative models. They sample from that distribution. So they would sample from the distribution that a foundation model would learn or a distribution that you give them. So these are your autoregressive models, your diffusion models, your Markov chain Monte Carlo models. They're trying to sample, get a representative sample from distributions and characterize those distributions. You have predictive models that, since I work mostly in the biological space, they map between different biological modalities, but it doesn't have to be biology, right? They're trying to predict the next event. They're trying to predict something about a new sample. AlphaFold 3, which is for protein models and protein structures, things that we think of as more standard canonical machine learning methods, random forests, support vector machines. These are supervised techniques that you're assuming that this model has already been built on a good sample from the distribution that's been learned, and you're looking to say something about a new event, right? A new sample. And then you have design models that will produce something desirable. So for example, if you're doing all your optimization techniques, Gaussian processes, what you're saying to them is you're saying, I want an object, or I want an individual from the distribution that has properties that I like. Can you give this to me, right? So for example, you might take AlphaFold 3 and say, I want the structure of a protein that would do X, Y, and Z. I don't know what it would look like, but if I give these desired traits to an optimization system and I put it on top of AlphaFold 3, maybe it can generate proteins with the structure that I'm looking for, that I desire, right? So these all do different parts of data discovery and modeling and prediction, right? So you can kind of put all these things together in a big system, right? Where you could say, I have a bunch of data of all these different types. The first thing I want to do is learn the distribution of the data, right? What does the data look like? It's kind of like exploratory data analysis, like on steroids, okay? Then you want to sample from that distribution, right? You want to figure out, like, what does this look like? If I sample from it, what kind of things do I get? Then you can do prediction, right? You can say, I want to predict an outcome for a new observation, right? Based on what I've learned. Or you can say, I want to get an optimal observation from that distribution. It might be something that's already in the data. It might be something that doesn't exist, but I'm looking to use all this data to solve a problem, and I need something with these certain characteristics. And so I'm going to use design models to generate that, right? And then there's this iterative process going on, right? Because at each step, you're going to get some result, and you're going to say, either this is fantastic, move to next step, or you're going to say, I tried building this foundation model, but it's not really working very well. And maybe I need more training data. Maybe I need more parameters in the model. So there's a ton underneath this, right? It's very simplistic, but underneath this is a ton of expertise and experience and choices that researchers have to make about how to implement this process. And then you're constantly improving it, right? Because there's new models coming out all the time. There's new data coming out all the time. AlphaFold releases a new version and you're like, oh, gosh, okay, fine. I have to now update everything I've been doing. So once we get to the end and hopefully we have something that's desirable, then it's time to go validate, right? And actually with each step, you're trying to do some type of validation, right? But in the end, you probably, if it's biology, you'd run to a lab and you try to do some validation of what you discovered. Okay, so there's this whole process underneath when people say AI, right? That it's kind of important to think about, and how it helps me to work in the space because I can categorize things and then I can be most useful to people when they have questions. Okay. Let me see okay, let me go next. Okay, so let's talk a little bit about the statistical perspective on AI because I get a lot of questions like, well, statistics isn't AI, is it? Or do you even do AI? Or how do you think about AI? Because researchers tend to think, oh, if I want to do AI, I should go to computer scientists, which valid, right? That's a great place to start. And if you're doing something that's modeling or sampling from data or whatever, of course, your statistics will come into it, right? So you really need the CS and the AI together to help you out. So here's an issue that kind of describes how statisticians think about modeling and how AI has, to a certain extent, turned things on its head. So this is Occam. He doesn't look very, very happy, but William of Occam was a Franciscan friar in the 12 and 1300s, and he was asked by the Pope, what are the theological implications of the church possessing a ton of material wealth? The church was very wealthy. The Pope was a little bit concerned about, does the church holding all of this wealth, is this consistent with the teaching of the Catholic Church, right? Is this appropriate that we have this wealth? And so Occam, being a nice Franciscan guy, said, okay, I'll go and study and I'll get an answer for you. Okay. And he came up after looking at all these reasonings and all these possible explanations for the church holding this wealth. And he basically said, look, I'm going to go with the simplest answer, right? There's all these potential answers to your question. Some of them are super complicated and twisted, and some of them are straightforward. I'm going to go with the simplest answer that addresses your question, right? So he's named for this philosophical tool called Occam's razor that advocates a principle of parsimony when deciding between two arguments. So his philosophical saying was, no plurality should be assumed unless it can be proven by experience, right? And the way we sort of translate this is go with the simple, right? Go with what can be supported by experimental evidence. You would choose something simpler and easier to justify versus a more complicated theory or model that takes more explaining and you might not have evidence to support. Okay, now, so Occam went back to the Pope and said, look, the simplest answer to your question is, it's not a good idea. The church really shouldn't be holding this kind of wealth. The church should be distributing this wealth to the people. It should be supporting the followers of the church. You can imagine how the Pope responded, let's just say, not happy. So he excommunicated poor William, and William had to flee from England and hide out in Saxony. The King of Saxony gave him shelter. So didn't end up great for William, but a good principle, right? So when choosing between models, we choose the simplest one that we can justify. Okay, makes sense. Okay, so here comes John Hickam. He was a physician at Grady Memorial Hospital in Atlanta. Grady is a enormous public hospital, and it does a ton of training of physicians. So it's a very big hospital, lots of medical residents. And at the time when he was working, so in the 1940s, 50s, 60s, Occam's razor was entering medical training, right? And it was encouraging physicians to stick to a simple diagnosis, right? If you have a choice between a simple and complicated diagnosis, go with the simple one. Okay. And so he's walking around the hospital, and he was helping train these physicians. And of course, he's walking around smoking. Everybody in the cafeteria is smoking. All the residents hanging out in their meeting rooms are smoking, and they're having the resident. He can see the residents having these discussions about trying to come up with the single diagnosis, right? So a lot of physicians took this to mean, oh, okay, I should try to come up with a single diagnosis that explains all of the patient's symptoms, right? And so they would sit and have these discussions over coffee and cigarettes about, oh, well, I think we could explain all these symptoms by like this diagnosis. And then someone would say, well, that really only explains like most of them, but they have this other symptoms. I think it could be this. And they were coming up with these completely insane diagnoses. And so he was like, wait, this doesn't make sense, right? Basically, sometimes it's complicated and you need multiple diagnoses, right? You might need multiple models to cover different areas of the data space. It's not always go with the simple, right? So his saying was, and he wrote an article on this, that a patient can have as many diagnoses as he darn well pleases, right? It can be super complicated, right? And he was explaining to the residents that it's statistically more likely that a patient has several common diseases versus a single rarer disease that explains the myriad of symptoms, right? It's much more likely that a patient has prediabetes, high blood pressure, and early signs of heart disease than they have Ebola. So it's like he was trying to tell them, dudes, like give the diagnoses that are necessary, right? So there's this tension between these two ways of looking at it, right? And when we're doing statistical modeling, predictive modeling, we have this same tension of goals. So it's a trade-off, right? So here's our trade-off, and this is how statisticians usually look at predictive problems. We say, goal one, your model has to be expressive, right? It has to capture the richness of the real data, right? So can't be too simple. Right? You got to try to capture what's going on in the data. Okay. However, goal two, you have to control statistical complexity, right? Make the best use of your limited training data, right? So yes, you would love to have a super, super complicated model that captures every aspect of the real data. However, you probably don't have enough data to support that. And so what we do is try to control the complexity of the model, right? Complex enough, but not too complex. And number three was be computationally efficient, right? And this came from many years of statisticians having limited computational power, right? Just you would want to fit a model to a ton of data, and you would go and start something running. And I mean, I can remember as a graduate student, like literally a week later, coming back to get your results, which may be required, but is very slow. And so there's this tension between these, right? So when I say don't be too complex, the way we think of this in statistical speak is keep the function class, so keep the model class simple enough so that sample averages the empirical risk, meaning the way you assess quality of the different models, right? Usually we look at like error, like sum of squared errors, right? Is a simple example, right? So that when you're doing your modeling on your data and you look at the error rates, you look at the sum of the squared errors, those should uniformly conform to expectations across the function class. What does that mean? That means that when I'm assessing my model and I'm fitting a bunch of data and I'm trying different models, what would really be unfortunate is if every time I got a new sample, the choice of best model kept changing. So every time I added a data point, I'd be like, okay, now it's telling me a completely different model is the best one. And then I would go get a couple more data points and it would say, oh, totally different model is now best. Oh, really, really difficult, right? What I want is that my model class is reasonable enough that given the data I have, the assessment from fitting the data to that, fitting the models to those data, the sum of squares errors I get is a good indication of the model quality, even if the sample size goes up, right? Even if sample size goes to infinity, I'm still going to choose the best model based on the data I have and the assessment from the sample of the risk or loss of each model, right? Okay. So these are the challenges, right, of statistical modeling, right? When deep learning came in and these enormous AI models, it was shocking to the statistical community, right? It was like, wait a second, you can you can fit a model with billions of parameters and it still works, right? It should, at some point, if the model's too large, it should overfit, right? And then you don't get good predictive performance. And so there was this puzzle of how can these models work, right? Two surprises. One was simple gradient methods seem to work. So things like gradient descent seem to give good parameter values, which is a little surprising because we always think of gradient descent as going to a local optimum and then getting stuck. So we're like, but it seems to work. And it gives near perfect fit to training data with almost no effort to control complexity and still does really well predictively. And a lot of us in the statistical community, like, heads blew off, right? It was like, what? So then we all thought about, okay, how can we explain this behavior? Because it's very different from what we've seen with our kind of traditional canonical approach to predictive modeling, right? And the way we look at it is that the model is so large and so flexible, and in many cases, the amount of data available is so large. You have so much training data that you can have a very complex model and you can essentially fit all your training data perfectly if you've captured the underlying form of the function generating the data, right? So it kind of means that if you have a flexible enough model and enough training data, you can make a model that what is kind of a combination of two pieces. One piece is the underlying function that's generating the data, right? This is what we would capture statistically. And on top of that, you can have all these little wiggles in your model that interpolate every little data point, right? And because that really complicated wiggly part doesn't really explain a lot of the variance, it's actually kind of small. It's a smaller contributor to the model than the bigger part, which is the underlying function space. You will still get good prediction, right? That little wiggly part isn't going to hurt you when it comes to prediction, but it means you can interpolate your training data, right? So you have something like on the left-hand side of this graph, which is you can see how this complicated model in green is capturing the underlying function, which is your gray dashed line, but it also has this fuzzy, very flexible part that is interpolating every little data point. That kind of a model will interpolate the trained data, but also predict well. If you have something like C, which is like polynomials, they're not wiggly enough, right? And so if you try to do interpolation with a polynomial, you don't have enough degrees of freedom. You don't have a big enough model class to interpolate and then predict well. You lose the ability to capture that underlying function, right? So this is kind of how we think about it a little bit in the statistical space. And I mean, I could give a whole course on whether this works or, turns out to be true in different type of AI models. But this is the basic understanding of like, yeah, if you have an enormous model, you can kind of get the best of both worlds a little bit. You can interpolate and get good prediction, which is super cool. The cost is the model's not identifiable, meaning because your model space is so big, you will often get many, many models that fit extremely well. And then you have the problem of which one is the better one, because they all seem to be doing well, right? So identifiability becomes an issue. Okay, so my last slide is just sort of looking at the overall space, how statistics interacts with these other fields. And that, for an example, if you're doing space-time modeling, which a lot of people are, you can use AI models and you can get good capture of complexity. You can capture nonlinearity, which is great. Not so good at interpretability, not so good at quantifying uncertainties, right? That's more of a canonical statistical approach. So kind of have to put some statistics into your process so that you can get a better sense of uncertainty quantification, right? Which parameters are good, bad? What are the confidence intervals around your parameters? And get better interpretability, right? There's ways to make your model a little simpler and easier to interpret. So it's this hybrid of these two fields. Okay, I'm going to pass it to Derek, and Derek, just let me know when you want me to turn the slides.
Sure. Thank you, Jennifer. So I will be presenting, or more accurately, representing slides from Amy Apon, who is a program officer with the National Science Foundation. She gave this presentation about a month ago at another meeting, and they focus on the National Science Foundation's perspective of the cyber infrastructure landscape targeted towards AI researchers. And I'm mostly going to be talking about, I know the slide says resources and funding for researchers, but I'm not going to be really talking about funding as it doesn't really apply to our European colleagues. I'm just going to be talking about the resources available for researchers in the US and how that's being approached. Next slide, Jennifer. And so just a little overview. The OIC Office of Advanced Cyber Infrastructure supports computing, data, networking, cybersecurity infrastructure for broad science and engineering. And so just kind of going around here a little bit, the research experiments that the NSF calls these the major facilities. They include places like LIGO, which is the interferometer both in Louisiana and Washington State in the US. They include Rubin, which I believe is the top left picture, which is the telescope in Chile. And the bottom left, for example, is the Event Horizon telescope, which they generated that image actually using some cyber infrastructure that I help operate. So I'm very proud of that picture of the wormhole in the middle of our galaxy. And then it also includes resources in the top left, computing, and those are just some pictures of some of the resources available. And then it also includes software frameworks and gateways, and then community building. The NSF sponsors various workshops and conferences in the United States. And you can go to the next slide as well. So there's many resources and services available funded by the Office of Advanced Cyber Infrastructure. And so some of these that I'll highlight is National Computing Data and AI Resources. So I'm going to talk a little bit about the NAIRR pilot, which has a platform there. I work for two of the other infrastructures here listed, Path, which for my European colleagues, you might be familiar with the Open Science Grid or OSG. Path is the non-Large Hadron Collider part of the OSG. And that's how that's kind of split out funding wise. And then also the National Research Platform, and I'm going to give a little bit of a demo on using the National Research Platform, which is an AI-based cyber infrastructure system, but it's actually highlighted here in these slides. There's various portals provided by and workshops provided by all these funded communities, and then there's also community workforce development, the Minority Serving CI Consortium, Campus Research Computing Consortium, and then Trusted CI. And I know Trusted CI works a lot with our European colleagues for cybersecurity issues. Next slide. So just a little bit about NAIRR, which is the National AI Research Resource Pilot. And so this was started about, I think, almost 2 years now. And it's infrastructure to drive AI innovation. And I have a slide coming up, well, more accurately, Amy has a slide coming up talking about all the resources available in there. But the goal is to accelerate US global AI leadership. And so a lot of the issues with is matching users to the correct resources. And so a lot of NAIRR is just about like steering users to the correct resources for them, so that they can be able to maximize their potential. And so we're building this AI ecosystem with NAIRR, and there's national and AI resources, regional resources, and then also there is training as part of this AI. So part of your allocation can be for like training and user expertise. Next slide, Jennifer. So just one example of this is, as part of NAIRR, the NVIDIA gave some allocation to their DGX cloud, which is this massive cloud of AI training resources. And so, but the problem is it's very difficult to use for like a regular user like you and I. It was built for the large companies out there in the world. It was built for the Citibank or JP Morgan. The people that can throw hundreds of uh, computer scientists at the problem, and make it work. And so there was some collaboration with UC San Diego to build kind of an easier interface uh, for the environment, to be able to allow researchers more easier access, maybe not to the full capabilities of the NVIDIA DGX cloud, but at least to the targeted ones that AI researchers are most interested in. And then part of NAIRR is also there's a lot of industry partners, which are coming up in a slide, but usually industry partners don't have the incentive or the capacity to do like reviews and manage allocations, and being able to partner with users to figure out what's the best match. And so that's part of what NAIRR brings to the table, is being able to partner with the industry and the researchers to be able to match them appropriately so that researchers get the resources that they need. Next slide, Jennifer. So these are some of the allocations that have been made across the country. There's a big map on the NAIRR website, which is nairrpilot.org. Researchers across the country are investigating different types of using NAIRR for different types of science. The large majority of it is, computer science, AI, intelligent systems, kind of what you would think. But there's a lot of other fields that are also using NAIRR, including astronomy, material science, biology. There's a little bit of physics, geology, ecology, and then on the left there's a map of where all the allocations have been made, and it follows pretty closely the population distribution of the United States. You'll see a lot on the East Coast and the West Coast, and then there's a few in the middle of the country where I'm from, and if your United States geography isn't great, which I don't blame you, the Nebraska is dead center in the middle of the country, and there isn't a dot right there in Nebraska, but there is actually a couple of allocations at Nebraska. The map just didn't map those quite right. And so there's on the order of about 266 projects, and a lot of them are industry supported as well. So not all of them are going to national supercomputers, for example. Next slide. So this is just like a brief overview of the website, nairrpilot.org. Basically, you fill out an allocation form, and then then it takes some time for review, and then they match you to the best resources. During your when you're filling out the allocation form, you do say like basic things like what is your research, what resources do you anticipate that you need, and kind of like what a summary of what makes you think that you need those resources. What preliminary things have you done to get to come to that conclusion? And part of the getting to that conclusion is the startup projects, which is the bottom left one. The startup projects in there, you get a small amount of resources, but It's very quick to review, and it only takes like a paragraph or two. Just saying this is kind of exploratory. We're just looking at what we will need in order to write a larger allocation if necessary. Next slide. As part of NAIRR, there's many data sets available, not only resources, but also data sets. So across the federal government, they have put out a call for all data sets that would be valuable. So for example, NASA has given out a lot of earth science data sets. There's also some from the census department, and then also like NOAA, which is the National Oceanographic and Atmospheric Administration, which is kind of like our weather forecasting here in the United States. They provide like tropical cyclone data sets to use for training or any interesting projects that may be come from these. Next slide. So these are the resources that are available. This is just a subset of the resources. There's a very long list on the website. They come from kind of, I would consider it like two different buckets. The ones on the left are federally funded like supercomputers in the traditional sense, both from the National Science Foundation and the United States Department of Energy. And so the different resources are listed there. Some of the large AI ones are Frontera at University of Texas at Austin, and then Delta, which is at the University of Illinois. And then also on the other side of the bucket is the industry partners. They're kind of everybody that you would expect kind of in the AI industry that have provided donated resources to this project. Available from allocation. I already talked about NVIDIA DGX Cloud, but you also have OpenAI that provides like ChatGPT credits. So if you want to query ChatGPT a lot from the AI in order to do maybe some AI understanding, deep model understandability tests, you can get millions of credits from OpenAI. Same with AWS, Microsoft Azure, Google, just kind of everybody that you would think of in the AI space provided. And the reason that a lot of these places provided them is I didn't talk about the origins of NAIRR, but NAIRR came from a presidential memorandum from the previous administration, and it has been NAIRR has continued under the new administration, and the presidential memorandum also meant that the White House was pushing these providers, these industry partners, to be part of this as well. And so there was some push and backing from the highest levels of the U.S. federal government in order to get these industry partners part of this. And that's why we have such a wide breadth of partners in there. Next slide. So I'm going to highlight a couple of the different projects that are part of NAIRR that provide resources. So this is the PATH, the Partnership to Advance Throughput Computing. I just want a conflict of interest statement here. I work for PATH. I'm funded by PATH partially. So PATH is what the Europeans might be familiar with is the Open Science Grid. PATH is the kind of the retail version for end users. So it's everybody that's not the Large Hadron Collider users. So PATH combines hundreds of different sites, and they provide kind of opportunistic access to the resources. PATH runs up to, I think, like 50,000 cores at some points. Just processing power available to anyone in the US. And there are GPUs available, but the PATH mostly focuses on throughput computing. So for example, the PATH PI is the same PI as HT Condor, if you're familiar with that technology. And so they're very into like throughput computing. So instead of running very few quick processes, they run many slower processes. And so they run on a huge amount of different types of resources across the United States. And they have hundreds of sites and just a wide buy-in into it. And then part of PATH is also the Open Science Data Federation, which has what they call caches and origins. And it's just a way to distribute data for open science that allows for regional caches so that the downloads are faster, and then origins are where the data custodial duties of the data actually reside. Next slide. And another resource that I'll be hopefully giving a demo here in a few minutes, as long as everything's working, who knows how live demos work, is the National Research Platform. So this is a distributed shared resource for research and education. This map is a little outdated. There's up to 100 organizations now contributing to the National Research Platform. It focuses much more on GPUs. So there's something like 1,500 GPUs in the National Research Platform. There's a wide variety of GPUs from the H100s, and we have a Grace Hopper as well, all the way down to we have gaming GPUs. We have 3090s and 4090s that are still very useful, especially for inferencing and various AI research. And so we provide different types of interfaces, which I will demonstrate here in a minute. And it's led by San Diego, University of Nebraska, Lincoln, myself, and then at the Massachusetts Green High Performance Computing Center, which is just outside Boston. Next slide. And then NAIRR Pilot also provides educational access. And I see my time is quickly running out, so I'm going to go quick here. And so classrooms can also ask for access to NAIRR for Jupyter notebooks, so that they can provide students with easy Jupyter notebooks and easy access to GPUs. Next slide. And then this is just one example of LIGO, of all the different infrastructure projects that they use. And so, you go from the actual experiment, in Livingston, Louisiana, and in Washington. And it just kind of goes through all these different experiment infrastructures to actually get to the picture that you see on the right, which is the kind of the artist illustration of a gravitational wave. And you'll see that all these different infrastructure projects that are funded by NSF, whether that's Pegasus, Globus, all these computing resources, Jetstream, Stampede, Comet, PATH, which I already talked about, National Research Platform, the Open Science Data Federation, Internet 2, which is the networking research and education network here in the United States. All these different projects touched this data in order to go from experiment all the way to result. And so LIGO is just one great example where they have such a large amount of data and computing needs that they do touch a tremendous amount of infrastructure. Okay, I think that leaves it to the demo. So I will go ahead and share. And caveat, live demos, we'll see how this goes. And so I just wanted to, this is the updated view of that map for the National Research Platform, showing all the different sites. And there are sites actually in Europe as well, mostly providing Open Science Data Federation caches, whether that's actually at CERN itself, or we have Czech and then UK and Amsterdam. But the vast majority of sites are in the United States. And if you're wondering where Nebraska is in Lincoln, it's right there in the middle of the United States. And then the National Research Platform and website is nrp.ai. And so it kind of gives a description of what National Research Platform is all about. And then, of course, we love our maps. If you have distributed resources, you love maps. And then, so one of the interfaces to the NRP is just a Jupyter notebook, which is kind of exactly what you would expect. You're able to start a Python kernel. And then I have or I already have a link here showing how this works. And this one that I started up, it's running on let's see, the driver versions here. And then it's running on a GeForce 3090, so it's actually running on a gaming GPU, this particular Jupyter notebook. And we have about 1,500 GPUs on the NRP. And so you would use this like any other Jupyter notebook running, PyTorch or whatever. You'll notice also on the launcher, we also have VS Code. So another option to interface is actually you start up like a VS Code interface to the resource. So if you're doing like development of CUDA libraries or something that uses CUDA or any sort of, you can do PyTorch in here as well. You get kind of your familiar VS Code interface. You have your normal terminal, normal editor, and you can have all your copilots or whatever type of interface here. And then one last interface that we have to the NRP is we have our own kind of chat GPT interface built on hosted open models. And so this, for example, this is an example that I did. We host several open models. This one's DeepSeek. But we have a lot of them. We have Gemma 3, which is out of Google, Llama, which is out of Meta, and then Quen, which is another one, and DeepSeek, which hit this summer, was kind of made a splash. And so we run these on resources on the NRP, and then we provide both API access, and then you can also use like the chat interface to access these open weight models. And that was kind of my demo. And so I'll go ahead and open it up to questions.
Wow, thank you so much. And many thanks to Jennifer, and Derek. And for Jennifer, you're very clearly to explain this fundamental shift from traditional statistic to AI approaches. So help us to understand how our scientific community is evolving in this age of AI. And then thanks to Derek for introducing the development in US cyberinfrastructure with really close parallel work we're doing in EGI. So we are we leave it to our audience to see, and any question I hope I see are there. If you have a question, and just raise your hand, we can directly talk to them. Really thanks for this experience from US. You already do many useful things for the community.
Yeah, I would say that from the standpoint of a researcher, right? So I can kind of put on my researcher hat as opposed to, your cyber infrastructure hat. From a researcher perspective, I would, I always encourage my colleagues and my students to, go talk to the people who work in cyber infrastructure. Go talk to if you have a high performance computing center, go talk to them, right? Reach out to these people, because I know that a lot of researchers and students who have not previously worked with high performance computing or NAIRR or these things, it can be very intimidating, just because it's not a world that they've interacted with before. And so their go-to solution for any computing problem will be, I can fix it myself. And that's true. I mean, to a certain extent, that's absolutely true. And, students and researchers should always do the, like, I can try to solve this myself. But at some point, if you're working with a lot of data and you're doing modeling and you want to get into using AI, having a trusted partner who works in cyber infrastructure is super, super important. And part of that is because the potential to waste resources and time is substantial, right? If you're just kind of new. And so just go talk to them, send them an email, right? They're there to help you. And if you explain to them what you're trying to achieve, they will point you in the right direction, right? It may turn out that your model doesn't work. It may turn out that you don't get the results you want, but you will be pointed in the direction of the appropriate resources and the appropriate training for what you're trying to do. So it basically puts your efforts targeted into the right direction, and you save a ton of time and effort just by having a conversation. So I tell my students this and my collaborators this all the time, and I often get the funny look, kind of like, oh my gosh, like you talk to those people? And I'm like, yes, right? They don't bite. They are there to help you. So send in a ticket, right? You will be surprised that they will be willing to work with you. And I think that's important that we just keep reminding people who come from outside of cyber infrastructure that, yeah, these are available to you, and it will be helpful, right? Yes, you'll learn a lot, and it will help your research. And so I always have to continually emphasize that, right? It's like telling students, go talk to your advisor. A lot of times they give me the funny look like, oh my gosh. And I'm like, you will come back with all your limbs attached, I promise. And they will help you, right? But it's a process, right? It's a process of, it's like any interdisciplinary enterprise. You have to get started, but it will benefit you. Absolutely, right? So just keep encouraging the scientific community to engage.
Thank you so much, Jennifer. That's the message we need to send to our community. This collaboration is important. Probably this AI time is bring us a new stage for this
Right.
more in deep collaboration. And I see Macro, you have some question. Can we enable Macro to talk and to have a directly discussion will be help. And Federico, I cannot handle from my side. Maybe you can unmute Marco.
Can you hear me?
Yes, we can hear you.
Okay.
Yes.
So Derek already answered in the chat. Yes, we are, let's say, investigating these same technologies because we are also building this LLM interface for our communities. Then I have many other questions. I don't know.
Well, Marco, if you have lots of questions, which is fantastic, Yin can share my contact information, Derek's contact information. We are happy to connect with you offline and address any questions that you have. I'm just looking at the time going, okay, I know we're going to wrap it up, but please, I encourage you to reach out to us by email or through Yin, and we can have further conversations on this topic. We're happy to do that.
Thank you. Thank you for the nice presentation.
Very
Yes.
welcome.
Thank you. And Marco is leading EGI AI infrastructure work. So definitely to encourage. Okay. And I do not see other hands, and then time is perfect, amazing. And thank you from Derek.
And Marco,
Wonderful.
I wanted to add one more thing. Purdue has kind of been doing some great things here in the US, and they have a Gen AI lab. They have a paper that they published. And they have a very unique infrastructure and very I think it's very well done, where users are able to like bring their own models, and then they get a chat interface that they want, and they can like fine tune. And they have a tremendous amount of they've done a tremendous amount of work on this at Purdue, and so they wrote a paper, and then I linked it there.
Yes, I captured the link.
Oh, great. Thank you, Derek. That's awesome. Okay.
Okay, and then I give a final thanks to Jennifer and Derek. Thank you so much. Really, really very exciting talk. Also give a thanks to all our audience, and thank you for your participations. And thanks to Federico, you work behind the scene and to support this. Have a good day. And then Jennifer and Derek, thank you so much. You have a good day and very
Absolutely. Thank you very much. Appreciate it.
you.
Thank you.
Thank you. Thank you.